Okay, welcome to the practice problems for isotonic and buffer solutions. And I know that doesn't sound very exciting, and well, it probably isn't very exciting, but that's not true. These are some interesting calculations to do. They're not easy ones, but it's an important section because as pharmacists, you're going to be preparing the drug products that are going to be used by patients. And in this example, these are going to be drug products often used as injections or ophthalmic solutions to be used in the eyes. And these solutions need to be compatible with the biologic tissues. So in this case, we are talking about compatible as far as tonicity and making these products isotonic or having the same tonicity as our blood or our tears or the biologic tissues that we're putting them in. We don't want our products that are formulated to provide a drug to not only provide the drug but cause problems because of tonicity. Or, in the last part of this section, we'll cover questions relating to buffer solutions because the active ingredients we often put into these injections or these eye drops, these drugs, are either weak acids or weak bases themselves. So if we just dissolve them in water, the pH of the solution we'd be placing in the eye or placing in the blood would not be compatible and cause problems themselves. So we need to make sure that the solution around which we put our active ingredient can not only ensure that it remains isotonic, but also buffer any sort of weak acids or bases the drugs might be to ensure a compatible pH. So while maybe not the most exciting topic, very important for correct formulations of drugs used, or certainly drug products that we're going to deliver as pharmacists. So with that, this lecture or the questions that I've put into this lecture are really divided into three areas. We're going to start by kind of dealing with the idea of what is a freezing point depression, and then we'll use freezing point depression as a way to formulate a isotonic solution. And then we're going to say, well, if we don't use freezing point depression, you can also calculate for isotonicity or those types of questions using what we call sodium chloride equivalent method. So that'll be the second section. And then we'll end with some questions that relate to the buffer solutions. So with that, we'll go ahead and get started. So this first question is about the freezing point depression. And we'll start with the question and then we'll explain what we're doing. The question says, atropine sulfate monohydrate is an electrolyte salt which has a molecular weight of 695, 3 ions, and an 80% dissociation. What is the freezing point of a 2% solution? Okay. Now, what the heck's going on here? Don't blow your mind here. I know there's a lot of information, but let's just do a little bit of background. Why are we talking about atropine? Atropine sulfate is an old drug. We've used it for decades or centuries possibly. It's actually a naturally occurring product that's extracted from a belladonna alkaloid. Now, atropine is the prototype antimuscarinic drug, and hopefully you've had a little bit of background with the autonomic nervous system. You know there's the sympathetic and the parasympathetic. Just understand that atropine blocks the muscarinic receptors, which means it blocks the function of the parasympathetic system. In the end, why do we care about that therapeutically? One of its main uses is as an eye drop, and it's used as an eye drop because it causes mydriasis or dilation of the pupil. So when you go to the eye doctor and they put those drops in so they can look inside your eye and look at your retina and do some things inside there, they're using a drug very much possibly like atropine, which is an antimuscarinic. So clearly we would need to be able to formulate atropine into an eye drop. As such, we would need to make sure that we're producing an isotonic solution. One of the ways to calculate and formulate things in an isotonic solution is to use the freezing point depression method that we'll talk about next. So for this question, we are focusing though on just this concept that putting drugs in solution into water affects the freezing point of that water. So the first thing I would talk about is I love this picture on the right hand side. The first concept about freezing point depression you need to understand is that if you take everyone understands that you take water freezes at 0 degrees Celsius. But did you understand that if you put stuff in the water, if you dissolve drugs and put substances in the water, it affects the temperature at which that water can now freeze? And I like this picture because it tells you that the more friends you have, the more they huddle around you, the more they keep you warm, the more they allow you to have a lower temperature before the water freezes. So the more particles, the more things in the water that can come together and keep themselves warm, the lower the temperature will actually freeze at. All right. So what do we mean by friends? We're talking about particles. And that's a little bit different than molecules. So if we took an example of a non-electrolyte like glucose, if we took 2 glucose molecules and put them in water, they don't dissociate, they stay together, so you still only have 2 particles. Well, 2 particles aren't a lot of friends to keep each other warm, so it's not going to reduce the freezing point depression very much. But what if we took the same 2 molecules, but did 2 molecules of sodium chloride, that is NaCl? What's different about a molecule of sodium chloride is it is an electrolyte, and so when it's put into water, it dissociates. It separates into its 2 components. So 2 molecules of sodium chloride actually produce 4 particles. 2 sodiums plus 2 chlorides gives you 4 particles. That's more friends to huddle together to keep warm. That means it's going to be able to lower the freezing point lower for the water. So just kind of, and now that's not technically what happens, but visually, I think that hopefully that gives you this idea. And you'll see that as we go forward, though. The more particles, the lower the freezing point before the water actually freezes. So getting back to this question, looking on the left-hand side, rewriting the information we're going to need going forward. This question says, the drug we're putting into the water is atropine sulfate monohydrate. It has a molecular weight of 695. When it dissociates, it produces 3 ions, and it dissociates at a rate of about 80%. And our target, in the end, we want to know the point at which the water will freeze when we use a concentration of 2% atropine. Okay, so I've rewritten some of that information here. What is the first step to all of this? Is that we must calculate the dissociation factor for atropine sulfate monohydrate. Okay, to do that, this is where it might blow your mind here a little bit, but we need to start with the fact that it dissociates at 80%. Now, to go forward, we need to imagine, to calculate this number, let's start with 100 molecules. So if we had 100 molecules of atropine sulfate monohydrate, those 100 molecules, and we put them into water, they would dissociate at 80%. That means 80 out of 100 molecules would dissociate. Okay? Now, when one of those molecules dissociates, what does it dissociate into? It actually dissociates into 3 ions. We were given that in the question, that it dissociates at 80%, and when it does dissociate, it dissociates into 3 things. And as you can see listed here, the 3 things are an atropine molecule, or ion, and sulfate ion, and a hydrate ion. So you will get 3 things for every 1 molecule that dissociates. And we said that there would be 80 out of 100 molecules that would dissociate because it dissociates at 80%. So right now, if we just start counting particles, not molecules, we started with 100 molecules, but if we count the number of particles yielded from those molecules, we would have at this point 80 atropines plus 80 sulfates plus 80 hydrates. We get 3 things for every molecule that dissociates, and 80 out of the 100 dissociated. The last thing to understand is, while we had 80 that dissociated, we had 20 that did not. So we still have those 20 things. Now they're just 20, they don't dissociate into anything, but we'll have to account for those as well. So the next step is just to add up all of those particles. So we have 80 atropines plus 80 sulfates plus 80 hydrates plus the 20 undissociated means we have a total of 260 particles. 100 molecules yielded 260 particles. So the last step of the idea is to just be able to calculate the dissociation factor by saying that the 260 particles is essentially divided by 100 that we started with, means we got 2.6 times as many particles as we started with molecules. So the dissociation factor is 2.6. We will get 2.6 as many particles as what we start with for atropine. That was part 1. Going forward to part 2. Pretty straightforward, but to go on to the next, part 3, we need to know what our target concentration of atropine is, but not as a percent. We need it in the units of grams per liter. And you don't know why yet. You'll see that on the next slide. But for now, it suffices to say that we were told in the question that we are going to have, or we want to know, for a 2% solution of atropine. Well, we need to change the units. We need to know that a 2% weight per volume is the same as 2 grams per 100 milliliters. It's the same thing by definition. Now, what we want is it per liter. So what we need to do is multiply by both the top and the bottom by 10. So we multiply 2 by 10, we get 20. We multiply 100 by 10, we get 1,000. So we are just re-expressing our concentration now, not per 100 mils, but per 1,000 milliliters. And that would be 20 grams per 1,000 milliliters. Well, 1,000 milliliters is the same as 1 liter. So essentially, we have 20 grams per liter. And all I'm trying to make sure you can see in this math is that a 2% solution is the same as saying we want a 20 gram per liter solution. It's the same concentration. But the two numbers going forward that we're going to need next are the dissociation factor, often abbreviated I, is 2.6. And our concentration, our target concentration, is 20 grams per liter. So I've carried that over on the rewrited information on top. Now, before we can finish this calculation, we need to define some things and be able to just say this is the fact we need to solve this question. Okay? So the first definition is to remind you that a mole, 1 mole of a drug, is equivalent to its formula weight in grams. So if I have 1 mole, I have the formula weight of that drug in grams. You should know that. Hopefully that makes sense. Next, we're going to say, what is a molal concentration? A molal concentration is simply saying we have 1 mole per liter. Okay? But remember from before, that also means we can restate that since 1 mole is equal to the formula weight in grams, then a molal concentration is also the same as the formula weight in grams per liter. That would also be a molal concentration. Why do we need to know that? Because the fact that we need to know is that the freezing point of a molal concentration of electrolyte solution is equal to negative 1.86 degrees Celsius times the drug's dissociation factor. Okay? Now, having said those facts, let's set those up in the way we're going to solve this question. Let's just restate those facts. We know that the formula weight of a drug per liter is equivalent to its molal concentration. So the formula weight in grams per liter is the molal concentration. We can set that over the fact that we know that concentration will have a freezing point depression of negative 1.86 degrees Celsius times its dissociation factor. That's from what we just said above. What you may not realize is that if we set it up as a proportion like this, we can now set that equal to some target weight per liter that we're interested in. Set up a target grams per liter so that the units match our formula weight per liter. But we can set what we're interested in on top, set that over some X. And that X would be the resulting freezing point depression caused by our target weight per liter concentration. All right? That may still seem a little weird. Let's set it up using the actual question. So, using what we just talked about, let's set it up and use real numbers. We're saying that because atropine has a molecular weight of 695 grams, that if we had a concentration that was 695 grams per liter, that is the molal concentration of atropine, that would have, we'll set that over its freezing point depression, which we would know would be negative 1.86 degrees Celsius times the dissociation factor that we calculated. Remember, we calculated the dissociation factor for atropine as 2.6. All right, so we can set up that ratio. What we can now do is set that equal to the concentration we're actually interested in, which is, remember, was 2%. But we said 2% is the same as 20 grams per liter. So now that's the target concentration we're interested in, expressed in the same units as on the left-hand side with the 695 grams per liter. Okay, so that's our target, 20 grams per liter. Set that over X, which is what we don't know is we don't know what that concentration would actually lower the freezing point, but that's what we're solving for. So now if we just cross multiply, we can solve for X. So if we took our negative 1.86 degrees Celsius times 2.6 times 20 and then divide by the 695, that would solve for x and show us that our final result for this question is that a 2% atropine sulfate monohydrate solution lowers the freezing point to a negative 0.139 degrees Celsius. Okay, so let's apply that information. That previous question was interesting, but the main point was so that you understand and can appreciate the fact that the more solutes that you have in a solution, the lower the freezing point depression it causes. And the reason that that is important at all is the fact that we do know that biologic fluids such as blood and lacrimal tissue, fluid I should say, has a freezing point depression of negative 0.52 degrees Celsius. They have enough stuff, enough solutes, electrolytes, whatever is in those biologic fluids. There's enough stuff so that the resulting freezing point depression is negative 0.52 degrees Celsius. Why is it important? So that when I make a solution of whatever I'm making for whatever drugs I need to add to these biologic tissues, if I want to make sure they're compatible as far as being isotonic, I just need to ensure that my final solution also has a freezing point depression of negative 0.52. So using this freezing point depression method, we can use it to formulate essentially isotonic solutions. So let's just do that with an example here. So let's look at the prescription first. The prescription calls for homatropine hydrobromide 1% ophthalmic solution. Okay, the amount of drug we want in solution is a 1% homatropine. Okay, we then want to add how much ever boric acid is needed to ensure that the final product is isotonic. And the final volume we want to make is 15 milliliters. Okay, so 15 milliliters of an ophthalmic solution, meaning it's isotonic and with 1% homatropine. And the question then asks for how many milligrams of boric acid are going to need to be added to ensure that it is isotonic in the end. All right, so to summarize the information we need to go forward is that we want a 15 milliliter of fluid that has a 1% concentration of homatropine and that is also isotonic. And to adjust the tonicity, we are going to use boric acid. All right. Now, to use the freezing point depression method, the next step would be to look up the freezing point depression caused by our specific ingredients that we are going to add. We're going to use both homatropine and boric acid. We can go to a table, and this table is straight out of the textbook, published resources, where they publish what they call a delta TF 1%. The delta T stands for the change in temperature, and the F stands for freezing. So we're talking about the change in temperature in terms of the freezing point of a 1% solution. So understand, for all of the drugs listed here, the value given in this table represents a 1% solution of that drug. So it's the delta TF 1%. And the drugs that we're interested in are the boric acid that we're going to use for the tonicity adjuster. Its delta TF 1% is 0.29 degrees Celsius. And then our active ingredient, homatropine, has a delta TF 1% of 0.11 degrees Celsius. And so you can see that I've written that down. So this is all the information we need to go forward to solve this question is right here. We've looked up the information we need. Now we need to use that information to actually calculate and formulate our eye drop. So first step, what is the first thing we're going to do is to determine the remaining freezing point depression needed. Okay, that's still a little mind-blowing. I'll remind you. First of all, what is the target? Our target is to make sure our final solution is isotonic with blood and lacrimal fluid. It has to have a final freezing point depression of negative 0.52 degrees. So that's our target. So the remaining must start with our target and subtract out what we already have. So what do we already know? We know from our table that our homatropine concentration we want in our final product is 1%. That's very convenient because the delta TF we looked up in the table was for a 1% solution. So we know 1% homatropine will reduce the freezing point by 0.11 degrees Celsius. And that's the only thing we're going to have in there to begin with. So let's start with this equation. What our final target is negative 0.52 degrees because we know that's isotonic. So from that, let's subtract the decrease of 0.11 degrees degrees reduced by the homatropine. So negative 0.52 minus negative 0.11 means what we still need to get is a reduction in freezing point of 0.41 degrees Celsius. So a 1% homatropine solution by itself would not be isotonic because it only lowers the freezing point by 0.11 degrees. What we need is to add something else that will lower it further an additional 0.41 degrees. And what we said we're going to use to do that is boric acid. So the next question is how much boric acid is needed to cause the remaining freezing point depression? Answer that question, we'll go back to the fact that what we looked up on the table was that boric acid had a delta TF 1% of 0.29. That means, and we'll set it up as a proportion, that on top, a 1% concentration of boric acid will lower, so on the bottom, the freezing point depression by a negative 0.29 degrees. That's straight out of the delta TF table. Okay? Now, what we can set that equal to is we don't know how much boric acid we need. That's what we're going to solve for. So X on top is the percent boric acid that we need, but what we do know is what's on the bottom. We need the amount of boric acid that will lower the freezing point depression by 0.41 degrees Celsius. So now if we solve for X by cross multiplying, so we'll basically just take 0.41 degrees divided by 0.29 degrees, we see that the final concentration that we would need is 1.41%. To summarize, 1.41% solution of boric acid will cause a freezing point depression of 0.41 degrees, which is what we need to add to the 0.11 degrees that is being lowered by the homatropine. Okay? So we're not quite done because the question did ask for the milligrams of boric acid. So our last step is to set up this formula, and I'll walk you through it. And it starts with the fact that the volume we're compounding is 15 milliliters. So if we want 15 milliliters to be a 1.41% boric acid, we have to start with 15 milliliters, multiply it by that concentration expressed as 1.41 grams per 100 milliliters. This way you can see that the milliliter units will cancel. And then the last step was to convert grams to milligrams. So we'll just multiply that by the fact that there's 1,000 milligrams per every 1 gram. So you can see our units will cancel. And if we do that math all the way across, we see that we need 212 milligrams of boric acid. If we took 212 milligrams of boric acid and put it into 15 milliliters, that would create a 1.41% solution. That solution would lower the freezing point by 0.41 degrees Celsius. By adding also 1% of homatropine, our active ingredient, would be the right concentration we want therapeutically, but that 1% would also reduce the freezing point depression by 0.11 degrees. 0.11 degrees plus our 0.41 degrees would cause a final freezing point depression of negative 0.52 degrees Celsius, which makes our final product isotonic. So hopefully this illustrates for you how you can use this concept of freezing point depression to be able to formulate a product such as an eye drop so that the final product has whatever drug concentration you want to be actively therapeutic, but you can add other ingredients to the sufficient amount to get the final product to be isotonic. For this next question, let's jump down past some of the details and just kind of get a feel for the question to begin with. The question for this one that we're going to do next says, how much of each ingredient would be needed to prepare enough solution to fill 510 milliliter bottles? So obviously, we're making a batch of 510 milliliter bottles of an eye drop. Okay, so if we jump back up, what is the actual eye drop? The eye drop is a product that actually contains 2 active ingredients called COSOP. The brand name of this is COSOP. The 2 ingredients are dorzolamide and timolol, and they're combined in this ophthalmic solution to be used for the reduction of intraocular pressure in patients with conditions like open-angle glaucoma or ocular hypertension. And this combination is actually useful because it produces a greater effect combined than either agent alone. And that's because they have different mechanisms of action. The dorzolamide is a carbonic anhydrase inhibitor, whereas the timolol is a beta blocker. So this drug combination actually works more effectively than either agent alone. So it's not the first line agent. You would try either one individual agent first, but if it wasn't strong enough, then the combination is definitely going to produce a greater effect. So it's a very useful product. Having said that, it makes a little bit more of a complicated product. So if we go back up and look on the ingredient list, we said it has 2 active ingredients, the first being dorzolamide, and we know we need a concentration of 22.26 milligrams per milliliter. The other active ingredient is timolol meliate at 6.83 milligrams per milliliter. There is a third ingredient called benzalkonium chloride, which is important because it is a preservative. It helps prevent bacterial growth or contamination. So we need a little bit of that in there to prevent that. So we need that at a concentration of 0.0075% weight per volume. And those are the 3 active ingredients. The problem is that all 3 of those active ingredients, when added up in those concentrations, may not make the final product isotonic with lacrimal fluid. Therefore, what we will also add is enough mannitol, which is simply an inert sugar molecule, but we're going to add whatever amount of that mannitol we need to make sure that the final product is also isotonic. So that kind of sets up what we're trying to create. The point to this question, though, is to use this alternative method. We've been talking about freezing point depression, but an alternative method for formulating isotonic solutions is the sodium chloride equivalent method. The relative tonic effects of 2 substances, that is, the quantity of one that is equivalent in tonicity to the effects of a given quantity of another, can be calculated. Now, most often sodium chloride is used as this reference substance since we know, or it's accepted, that 0.9% or 0.9 grams per 100 mils of sodium chloride is isotonic to both blood and lacrimal fluid. Therefore, this E value, this equivalent value for sodium chloride, for many drugs has been determined and been published, but it's defined as the grams of sodium chloride equivalent to 1 gram of drug. So if you saw or were given an E value of 0.5, that would mean 0.5 grams of sodium chloride per gram of drug. This method, therefore, is useful for determining the sodium chloride equivalents of all of the active ingredients. Can be used to determine how much additional substance, in this case mannitol, might be needed to add to make the final solution isotonic. So that's the method we're going to use for this calculation, is the sodium chloride equivalent method. So let's get started. All right, so here's a lot of that information rewritten. The first thing we need to do, however, though, is simply obtain the published E values. So if we have E values for all of these ingredients, this is going to be a very simple question. So we go to our published literature sources, in this case, right out of your textbook, and we see that I can find 3 out of the 4 E values. So for benzalkonium chloride, I see from the textbook it has an E value of 0.16. For mannitol, it has a sodium chloride equivalent or E value of 0.18, and timolol meliate has an E value of 0.14. So, almost got them all. The one that we're still missing, though, is the dorzolamide. So before we go on and deal with that fact, I just want to make sure you understand while we're looking at this. If we use timolol as an example, since it has an E value of 0.14, we know that means that 0.14 grams of sodium chloride are equivalent to 1 gram of timolol. I just cannot emphasize enough that when you are given an E value, you know how to express that in its units. And the E value is grams of sodium chloride per standardized gram of drug. All right, so we got 3 out of the 4. The problem is now we're going to have to actually determine the E value for dorzolamide since it wasn't available in the published literature. To do that, it's kind of a 2-step process. The first thing we're going to have to do before we calculate the E value is to calculate its dissociation factor. And we were given enough information to do this. And we have done this calculation previously in this lecture, so I'll just kind of more quickly go through it. The information we need to calculate the dissociation, or I, factor is its percent dissociation, which we said was 78% in the question, and the fact that when it does dissociate, it dissociates into 2 ions, or 2 particles, if you will. Okay? So to address this question, we're going to say that, okay, if we started with 100 molecules of dorzolamide hydrochloride, we know that it would dissociate at 78%. So 78 molecules out of the 100 would dissociate. And when it does dissociate, it will dissociate into 2 things. We were told it produces 2 ions. So the 78 dorzolamide molecules dissociate into 78 dorzolamide ions plus 78 hydrochloride ions, because we were told it forms 2 ions. Okay? Now, the other thing we have to address is the fact that while 78 out of the 100 molecules did dissociate, 22 of them don't, but they're still there, so we have to account for them. So we have 22 undissociated particles. So in the end, what we would expect to see if we put 100 molecules in solution is that since it dissociates at 78%, we'd get 78 dorzolamide ions plus 78 hydrochloride ions plus the 22 undissociated ions, meaning we'd have a total of 178 particles. And since we started with 100 particles, we take our 178 particles divided by, 100 molecules, we are essentially saying we are producing 1.78 times the number of particles than we started with molecules. Since we started with 100 molecules, ended up with 178 particles, we produced 1.78 times as many particles. Therefore, the dissociation factor is 1.78. Now that we know that, we can go ahead and calculate the E-value for dorzolamide. And we do that, remember, this E-value is comparing it to sodium chloride. So to do that, and I don't want to explain where this formula comes from, it's in your textbook, but to calculate the E-value, this is all you got to do. You're going to start with the formula weight for sodium chloride, which was 58.5 grams. We divide that by its published dissociation factor for sodium chloride, which is 1.8. We are then going to multiply by the dissociation factor of our drug, in this case dorzolamide, which we just calculated to be 1.78. And then we divide by the molecular weight for dorzolamide, which was given to us as 360.91. So if we do all of that math, we get a final value of 0.16. And I'll remind you that is the E-value, which means that we get 0.16 grams of sodium chloride per every 1 gram of dorzolamide. Now we have what we need to go forward. And I've re-summarized that here. For each of our 3 active ingredients at this point, we know the concentration we need and we know their E-value. All right? The next step is actually just a slight step backwards, is that before we go any further, we have to remind ourselves, what are we trying to prepare? What is the total volume of this ophthalmic solution we want to prepare? So I'll just refer back to the main part of the question, which said, okay, we want to prepare 500 bottles, and each bottle is going to have 10 milliliters. So 500 times 10, units cancel, we'll get 5,000 milliliters. So remember, for all of our active ingredients, we are trying to prepare a total volume of 5,000 milliliters. Now, we can actually calculate the amount of each active ingredient we need. Now, I put all the equations for all 3 active ingredients because they're all solved in the same way. So we'll kind of step through them all together. It starts with the fact that regardless of the ingredient, for all of them, we're trying to prepare a total volume of 5,000 milliliters. So we'll start with the 5,000 milliliters, and then we'll multiply by the concentration, which is kind of straightforward. But realize for dorzolamide, and you can look up above there, it said the concentration we want was 22.26 milligrams per milliliter. For timolol, it was 6.83 milligrams per milliliter. The little bit of a trick here was the question gave us the concentration for benzalkonium chloride as 0.0075% weight per volume. So the bit of a trick you need to understand is that percent weight per volume is the same as grams per 100 milliliters. So we simply rewrite the percent as 0.0075 grams per 100 milliliters, since it was given to us as a percent. Next, for the top 2 drugs, the dorzolamide and timolol, we actually want to express our final weights in grams, so we'll need to convert milligrams to grams. So for those 2, we're just multiplying by the conversion of 1 gram over 1,000 milligrams, so that the units of milligram cancel, and that our final math, when we do all of that all the way across, well, our final answers will all be in grams. And what we can see is that in the end, to prepare 5,000 milliliters, we would need to have 111.3 grams of dorzolamide, 34.15 grams of timolol, and 0.375 grams of benzalkonium chloride. Okay, so I've rewritten that information here on top. You can see the weights we need for each of our 3 active ingredients, as well as their E-value. Because now we're finally ready to convert from the amount of drug that we really are going to have in there to the equivalent amount of sodium chloride in terms of the amount of tonicity the drugs would produce. So to do that, we are going to use the E values. And again, all three active ingredients are solved for the same way, so we'll do them together. We start with the actual weight of the active ingredient that we're going to have in our 5,000 mils. So we start with that weight that we just calculated, and we are then going to multiply by their E value, expressed as grams of sodium chloride over per gram of drug. That way you can see that it's the grams of drug units that cancel, and we end up with grams of sodium chloride, essentially equivalents. So if we just multiply that across, what we're saying is that for dorzolamide, 111.3 grams is equivalent to, osmotically, in terms of the tonicity, it is equivalent to having 17.8 grams of sodium chloride. On the other hand, 34.15 grams of timolol is equivalent to only having 4.78 grams of sodium chloride. And the amount of benzalkonium chloride we're using, the 0.375 grams, is equivalent to only having 0.06 grams of sodium chloride. So the next step is simply to add up all of those. Since all three of those active ingredients are going to be in our final solution, we're going to have a total sodium chloride equivalent of the 17.8 grams from the dorzolamide, plus the 4.78 grams from the timolol, plus the 0.06 grams from the benzalkonium chloride. So all of our ingredients will produce a total equivalent amount of sodium chloride of 22.64 grams. You think, okay, that's okay. Is that enough? Is that all we need? How much do we need? That's where we need to go to next. So what we need to now know, the next step is essentially to calculate the total sodium chloride we would need to make our volume isotonic. Pretty straightforward. We know that we're going to be preparing 5,000 milliliters. We also know that an isotonic solution of sodium chloride is 0.9%, which means 0.9 grams per 100 milliliters. If we set it up this way and we multiply across, we see that milliliters cancel, and we would need a total of 45 grams of sodium chloride to make 5,000 milliliters isotonic. So that's our target for sodium chloride. So it should make sense that our next step is to take our target and subtract out the amount we're already getting so that we know what we're still going to need to get from our mannitol. All right. So we just said that we are going to need for 5,000 mils a total of 45 grams of sodium chloride. We subtract from that what we just calculated on the previous slide of 22.64 grams of sodium chloride is the equivalent amount that we're getting from all of our active drugs, which means what we still need to add is essentially 22.36 grams of sodium chloride to make our final 5,000 mils be isotonic. Well, we're not going to add sodium chloride itself. What we said we were going to add in this case to make the final product isotonic is mannitol, whatever amount of mannitol we need to be equivalent to 22.36 grams of sodium chloride. How do we figure that out? Well, we figure that out by using the E value again, because we had the E value for mannitol. But in this case, we're going to actually divide by it instead of multiply. So let's just set it up so you understand why. We need 22.36 grams of sodium chloride. We're going to multiply this by the E value expressed as 1 gram of drug divided by 0.18 grams of sodium chloride. So we're expressing the E value in this way so that you can see that the units of grams of sodium chloride cancel. And by multiplying across like this, we are essentially going to get grams of drug. So if we took 22.36 grams of sodium chloride divided by 0.18, so the units cancel, we'll see that that equivalent amount of mannitol would be 124.2 grams of mannitol. That says that amount of mannitol produces an equivalent amount of the 22.36 grams of sodium chloride, which is what we wanted. And essentially, we're done with our calculations. But this was such kind of an intense question. Let's just summarize what we did. Remember, we wanted to make 5,000 milliliters of this solution. All right. To do that, to make the right drug concentrations for our active ingredients, we would need to put in 111.3 grams of dorzolamide and 34.15 grams of timolol and 0.375 grams of benzalkonium. Those three things dissolved in and dispersed in 5,000 milliliters would produce exactly the therapeutic concentrations I desire. However, Those three things alone would not produce an isotonic solution. So I'm going to add an additional 124.2 grams of mannitol, which does nothing but produce the tonicity or the tonic effects I need to ensure that my final solution is isotonic with lacrimal fluid and won't cause any irritation or problems. And that is the end of this, I think, somewhat complicated question. The last couple of questions in this section transition from isotonicity calculations to actually are about calculations about buffer solutions. And so your first question is, why are we talking about buffer solutions and not isotonicity? Well, if you think about the compounded products that we would make to be applied to biologic tissue like IV fluids, or let's just focus on even eye drops. So we're going to be making solutions, formulating solutions to be placed into the eye. So clearly our solutions need to be isotonic. We don't want to cause any irritation or problems due to tonicity issues. And so we've just finished discussing those calculations. But think about this. Almost any active ingredient that we're going to want to dissolve in our eye drop, when it dissociates, it forms either a weak acid or a weak base, such that even though it was isotonic, it might reduce or increase the pH enough to make the solution irritating to the eye or to whatever biologic tissue we place the solution in. So we also need not only make them isotonic, we need to ensure that the final pH of our solution is within a neutral or a physiologic pH range. And again, some of our active drugs can change that. So we also want to ensure that we include buffers into our solutions to keep the pH, because just a reminder, in chemistry, a buffer solution serves to maintain a stable pH when a small amount of acid or base is introduced in the solution. And actually, in pharmacy or biology, sodium phosphate actually serves as a really good buffer solutions that you'll see used a lot of times in pharmacy. So let's look at this question. The question asks us to calculate the pH of the following buffer solutions. So we don't have to figure out the buffer. There are very standard formulas to use. So the prescription calls for us to use 6.2 grams of dibasic sodium phosphate in combination with 4.5 grams of monobasic sodium phosphate. You take those two solid ingredients, mix them together, and then we're going to dissolve them into a final volume of 1,000 milliliters. So that's the formula for our buffer solution. And the question just wants us to calculate the pH of the solution that results when we do that. Well, we'll need some additional information. So some additional information is as follows. Let's do this one at a time. Our two ingredients. The first ingredient to discuss is the monobasic sodium phosphate. What you absolutely need to understand about that is first the formula, and that the formula is NaH2PO4. Understand that when you put that in solution and it dissociates into its ions, it will produce one sodium molecule and one monobasic phosphate, which is the formula H2PO4. And just understand that why that has a -1 valence. Remember, phosphate itself, the PO4 part to that, is -3. And since you have two hydrogens and each one is a +1, that means +2 with the -3 means that's why the valence of the monobasic phosphate is -1. Okay? Very important to understand. I'll describe a little bit more why here in a minute, but this does serve as the acid in our buffer solution. Okay? And since it is the acid, we can determine, or we know its pKa is given to us. Since it's the acid portion, the pKa for the monobasic sodium phosphate is 7.21. And its molecular weight is 120. A lot of information there. Now, the second ingredient is the dibasic sodium phosphate. The formula for dibasic sodium phosphate is Na2HPO4. Therefore, when it dissociates into its ions, you'll get two sodium molecules and one molecule of the dibasic phosphate, which is H, which is a +1, and PO4, which is the -3. Therefore, the dibasic ion itself has a -2 valence. Because it is more negative, it has a -2 versus the -1, that's why the dibasic sodium phosphate serves as the base in our buffer solution. It's the base because its more negative charge means it more readily will accept an additional hydrogen ion. And therefore, accepting the hydrogen ion makes it serve as the base in this buffer solution. We also know that its molecular weight is 142. Okay? Even at this point now, I know for most pharmacy students, you're going to seem a little overwhelmed. This is a lot of chemistry. This is a lot of facts. You're starting to kind of freak out a little bit. But remember, what I need you to do at this point, take a deep breath and remain calm and just apply the Henderson-Hasselbalch equation. So, you've seen this equation many times, I'm sure, in chemistry. Relax. When anything relating to pH, you can usually rely on this formula, which says that the pH of a solution is going to be equal to the pKa plus the log of the concentration of the base in the solution divided by the acid in the solution. So remember, all buffers have an acid portion and a base, often referred to also as the salt part. But we'll say acid and base. Now, that's why it's so important to understand that in this solution that we are making, the monobasic sodium phosphate will serve as the acid. The dibasic will serve as the base, and that's because the dibasic is the one with the more negative valence, the -2, the one that can more readily accept a hydrogen ion. So monobasic acid, dibase is the base in our buffer system. Having said that, looking at that formula, really what we have to do now is just determine the concentrations, the relative concentrations of both our acid and the base. So let's do that. I've recopied some of the information from the previous slide, but clearly what we need to do now is to determine the molar concentration of each of our ingredients. So we'll start with the monobasic sodium phosphate, and per the formula there, we can see that we're going to start with 4.5 grams. Now to convert that to moles, remember we're going to multiply by the formula weight in a format of every 1 mole on top for every 120 grams, which comes from the formula weight. And we essentially set it up like this so that the units of grams will cancel and we'll end up with moles. So if we take 4.5 grams and divide it by 120 grams, you can see that we will have in our buffer solution 0.0375 moles of monobasic sodium phosphate. All right, let's do the same thing for the dibasic sodium phosphate. We were told to start with 6.2 grams. And if we multiply that by the fact that in every 1 mole, there is a formula weight of 142 grams, therefore grams will cancel. So 6.2 divided by 142 tells us that we have 0.0437 moles of the dibasic sodium phosphate. Easy enough? Part 2 is that we're going to now actually calculate it in a molar concentration, but we need to remember and absolutely fix in your mind which is the acid and which is the base. So let's start with the acid. Okay, the acid component in our buffer solution is the monobasic sodium phosphate. So let's take the moles of the monobasic, which we just calculated at 0.0375 moles, and divide it by the volume that we're compounding, which in this case in the formula was 1,000 milliliters. Understand that 1,000 milliliters is the same as 1 liter. So our actual concentration in molars is 0.0375 molar, because that's the number of moles per liter, which is what we just made. Now, let's do the same thing for the base. The base in buffer solution is the dibasic sodium phosphate. We take the moles of that we just calculated at 0.0437 moles, divided by the volume we're preparing, which is 1,000 milliliters. And since that is the same as 1 liter, our concentration is 0.0437 molar. We now know the molar concentration of both our acid, which is the monobasic, and the base, which is the dibasic. So the next step is simply to go ahead and calculate the pH using the Henderson-Hasselbalch formula. I'll remind you, there's the formula there. Now, on the left, let's go ahead and put numbers in that actual formula. So what we're really saying at this point, before we do any math, we can set up the equation as the pH equal to 7.21. And I'll remind you that's the pKa value that was given to us for the acid in our buffer solution, which I'll remind you is our monobasic. So again, the monobasic sodium phosphate pKa is 7.21. So that's where that number comes from. Plus the log of, and this is where we just need to get the right concentrations in the right spot. So it's the base over the acid. So we said that the monobasic is our acid, and the calculated concentration we had for that was 0.0375. So we put that in the denominator. The concentration of the base goes in the numerator. So our dibasic sodium phosphate concentration was 0.0437 molar. So now we set that up. If we just do that math and divide the base concentration by the acid concentration, we can see that just doing that little bit of the math, we get 1.165. Okay, so we're going to have 7.21 plus the log of the value of 1.165. So one step in the math on that means that's the same as the 7.21 plus 0.07, since that's the value that you get from taking the log of 1.165. So if the last step is simply to add those two numbers together, we can see that our final pH is 7.21 plus 0.07 for a final value of 7.28. So, to summarize, if we take 6.2 grams of dibasic sodium phosphate, mix it with 4.5 grams of monobasic sodium phosphate, dissolve that into 1,000 milliliters, and once it's all completely dispersed and dissolved, we use a pH meter. The pH of that resulting solution would be 7.28. Now, the whole point to doing and creating a buffer solution is to be able to buffer an acid or a base. So the last question, we'll take that solution we've just done those calculations for and ask this question. What would the pH change be if we were to add 3 milliliters of a 5 molar concentration of hydrochloric acid? So if we add 3 mils of 5 molar hydrochloric acid to the buffer solution we just calculated for, what would the change in pH be? Hopefully, the buffer will kind of keep the pH from making a significant change, but let's see what that change would be. So I'll remind you, this is the additional information that I'm carrying over from before. As a reminder, our acid in our buffer solution, the acid is the monobasic sodium phosphate, and we calculated its concentration again to be 0.0375 molar. The base in our buffer solution was the dibasic sodium phosphate, and its concentration was 0.0437 molar. And the final pH of that combination before we add anything, we just calculated to be 7.28. Okay? So now we're ready to proceed on with this question about what happens if we add 3 milliliters of a 5 molar hydrochloric acid solution. So our first step is actually to take that amount of hydrochloric acid and express it in terms of the amount or the number of moles that we're adding to our buffer solution. So let's start with this formula. And this formula comes from the fact that we said in the question that we're going to be adding 3 milliliters of this hydrochloric acid. And the next part is that the concentration of the hydrochloric acid was told to us as 5 molar. What that means is 5 moles over 1,000 milliliters. That's what molar means. And by multiplying in this manner, you can see that milliliter units will cancel, and our final answer will be in moles. So if we take 3 times 5 divided by 1,000, that is equal to 0.015 moles. All right. Now the next step is to express those moles in actually molar concentration. And to do that, we need to simply take the number of moles that we just calculated and divide it by the final volume. And I'll remind you that our buffer solution was made up to a total volume of 1,000 milliliters. Now, it makes sense, and you're absolutely right to say, well, if we take 3 mils and add it to 1,000 mils, our final volume is 1,003 milliliters. But in this question up above there, I kind of skipped this. We're going to go ahead for the simplicity of our numbers, ignore the volume displacement by the 3 mils. We're going to say that 1,003 mils is not significantly different from just 1,000 mils. Now, that's kind of an assumption here, but let's use that so that our numbers stay relatively nice. So, essentially, we have 0.015 moles in a final volume of 1,000 milliliters. Therefore, we really are adding 0.015 molar of hydrochloric acid. From that, we can proceed on, but that was the important first step. Now, things get a little crazy, because regardless of the numbers at first, you need to understand chemically what is happening when you add these 3 things together. And so I'll remind you, the 3 things that are in this question is the hydrochloric acid that we're adding to the solution that already contained the dibasic sodium phosphate and the monobasic sodium phosphate. And the reason we need to understand this, what we're leading up to, is we need to know how adding the hydrochloric acid will change the relative concentrations of our dibasic and monobasic sodium phosphate. To understand that, you really do have to write out the chemical formula for the reaction that's occurring. So that's expressed here. This is a little bit of chemistry. So, for example, if we just use an example starting with 1 molecule of hydrochloric acid, or HCl, the hydrochloric acid is going to react with the base in our buffer solution. The acid will react with the base. So our acid is the hydrochloric acid here. It will react with the dibasic sodium phosphate, which we said was the base in our buffer solution. The formula for the dibasic sodium phosphate is Na2HPO4. So when that reacts with the hydrochloric acid, what essentially happens is that the hydrogen ion, once the hydrogen chloride dissociates, and hydrogen ion will displace one sodium molecule from the dibasic sodium phosphate. As a result, that sodium that got displaced will react with the chloride from the hydrochloric acid and form a sodium chloride or salt molecule. On the other hand, the hydrogen that gets incorporated into the phosphate molecule changes then the formula to NaH2PO4 with the additional hydrogen. Well, NaH2PO4 is essentially monobasic sodium phosphate. So what you can see in this formula is that for every one hydrochloric acid molecule, we will decrease the base, dibasic sodium phosphate, by one molecule. But in the other side, while we create a sodium chloride molecule, we also increase or create an additional monobasic sodium phosphate. So let's put some numbers to this because we know the concentrations that we're starting with. When we add our hydrochloric acid, we are adding 0.015 molar. Okay? We know that our dibasic sodium phosphate in the very beginning starts with a concentration of 0.0437 molar. And that our starting concentration for this the monobasic sodium phosphate is 0.0375. That's what we had, and there was no sodium chloride or no salt to begin with. What happens with this reaction is all of the hydrochloric acid will be used up and will react with. All of the hydrochloric acid will react with the dibasic sodium phosphate and use up. So every one molecule of hydrochloride will react with and use up and take away essentially one dibasic sodium phosphate. So we need to subtract the concentration of the hydrochloric acid from the dibasic sodium phosphate since every molecule will use up one of each other. So our starting of 0.0437 will be reduced to 0.0287 molar for the dibasic sodium phosphate. On the other hand of the formula, while we use up the dibasic, for every dibasic that gets used up, we actually create a monobasic. So we increase the monobasic sodium phosphate by the same concentration of the hydrochloric acid we've added. So we're going to add to that 0.015 so that we increase our sodium phosphate monobasic concentration to 0.0525. Okay? So to summarize, what's happening in this reaction is that we essentially, the hydrochloric acid reacts with the base and decreases it so that our concentration after the reaction of the dibasic sodium phosphate has been reduced down to 0.0287 molar. On the other hand, our monobasic concentration has increased to a concentration of 0.0525 molar after the reaction with all of the hydrochloric acid. So again, our base concentration decreased while our acid concentration increased by the amount of the hydrochloric acid we added to the system. Now that we know what the changes in these concentrations are, we can go on and answer this question. And our final question was related to pH, so we stay calm and we know that we answer pH questions by applying the Henderson-Hasselbalch equation. So I'll remind you, that's what the equation is. It hasn't changed. Let's put our somewhat revised numbers into that equation. So what we have here is that the pH is equal to the 7.21, which is the pKa, which doesn't change, plus the log of, but now we need to make sure we put in our revised concentrations. And we said on top is the base, and the base concentration is now down to 0.0287 molar. On the other hand, our new acid concentration has gone up to 0.0525. So if we just do that math and divide those two numbers, we'll see that we get the log of a concentration of 0.547. Now, just be aware that that value actually is a negative number. The log of 0.547 is a negative 0.26. Therefore, that's why what we do in our second to the last step is the pH is equal to our pKa of 7.21. Now, though it looks like minus, because it's a negative number, 0.26. So if we do that math, we can see that the final pH of this solution is going to be 6.95. And it should make sense that it's lower. We've added some acid, we've used up our base, and therefore the pH has shifted to some extent to a lower value, a more slightly acidic value. However, that's still a relatively narrow change given the amount of acid that we added. Our buffer solution was able to really handle a lot of that hydrochloric acid. Now, the last part, though, is that the question didn't ask what the resulting pH would be. It wanted to know what the change in pH would be. So to calculate the change in pH, it's pretty straightforward. All we need to do is start with the pH we had before we added the hydrochloric acid, which we had calculated previously to be 7.28. And subtract from that the pH that results after we add the hydrochloric acid, which we said was 6.95. Therefore, the change in pH that resulted from the addition of that hydrochloric acid was 0.33 units. And those units were essentially towards the acid or towards a lower pH value. Hopefully you found these questions helpful. And just as a reminder, this whole section was about formulating solutions to be applied to biologic tissues like eye drops or IVs. And when we add our drugs, which can be either acids or bases, our final solutions that contain those therapeutic agents need to maintain an isotonic tonicity level and also need to be buffered to ensure that the pH remains within a biological compatible value. So hopefully you find these questions helpful.